Hello everyone, welcome to the course on artificial intelligence in industrial and management engineering. We have talked about the fundamental concepts of job shop scheduling and facility layout examples, right? So today we will try to introduce the basic concepts of metaheuristics, and we will talk about genetic algorithms, which is one of the metaheuristics that is widely used for solving these kinds of NP-hard problems. So when we were talking about facility layout problems, we have showed you various kinds of layouts that are available for designing your production system and the facilities that you have. Then we introduced you to how to design a single process layout or a single product layout. Today we will give you a basic example of the facility layout problem, and then we will try to solve that problem with linear programming example, with linear programming formulation, and then we will start learning about genetic algorithms. After that, we will show you a Python implementation of the same genetic algorithm for the problem of facility layouts to solve that by utilizing the genetic algorithms solution approach. Okay, so let us start by introducing a simple facility layout example. So let's say we have two departments. And we have two locations. Okay, so these locations are L1 and L2, and these departments are A and B, right? So material flow between departments are known. Distance between locations is known, and the goal of this problem is to minimize the total transportation cost. And what is the formula for calculating this cost? This is flow into distance, right? So we need to assign these two departments to these two locations, right? So step 1, first acquire the data, right? So flow matrix is F is equal to 0, 30, 30, 0. Okay, so here 30 units move from A to B, and 30 units move from B to A. Okay, and distance matrix is so this is your location 1, this is your location 2, this is location 1, this is location 2. So L1 to L1 distance is 0, L1 to L2 distance is 10, L2 to L1 distance is 10 again, and L2 to L2 is 0. Okay, now you have the data with you for the distance between departments and the amount of quantities that is flowing between departments, right? Now the next step is to create decision variables. Okay, so let's say x is our decision variable and the subnotations are ij. So what it denotes is this xij variable is a binary variable, so it will be only 1 and 0. Now when will it hold the value 1 if department I gets assigned to location J and 0 otherwise, right? Okay, so here I belongs to A comma B because I denotes departments, and J belongs to your L1 comma L2 because these are the locations. Now you have the data with you and the decision variable. So the next step is to create your objective functions, what you want to do in this little example. So this is your step 3. So this is the objective function. So in this example, what we are doing is we are moving some material from one location to another. So there is a cost involved, and wherever there is a cost involved, we need to minimize that cost. So we need to minimize the cost. Let us denote this cost with Z. So Z is your flow between I comma K and your distance. So this is your cost. This is J comma L and your decision variable of assigning I comma J and K comma L, right? So the summation of the cost that we get by calculating this product by utilizing these two decision variables, right? So for two departments here, this will result into Z is equal to 30 into D L1 L2 into your decision variable, that is x a L1 into x b L2 plus x a L2 into x b L1, right? So this is, since there are only two departments and two locations are involved, so it reduces to a very simple formula that you can enumerate and just write it by hand, right? But usually this is not the case. When this problem evolves and extends to more departments and more locations, then your computation power of your machines needs to be utilized, and the solution space extends to a whole new lot of possibilities, right? So this is finally your objective function. So in those conditions, when your solution space increases, you need to utilize different kinds of solution approaches like heuristics or meta heuristics. We will look into that, but now let's moving towards the next step, that is step 4, and here you want to introduce your constraints, right? So the first constraint is that each department can only be assigned to exactly one location. So this is your constraint in wordings. You need to convert these wordings into your mathematical formulation. So this can be written in mathematic notation as your decision variable x. If your department A is assigned to location 1, or your x department A can be assigned to location 2 is equal to 1. Since your x is a binary variable, right? Remember that your x is a binary here, binary decision variable. So x can be either 0 or 1. So this first constraint tells you that either A gets assigned to location 1 or A gets assigned to location 2. If both of this is assigned to 1, then this equation will not follow, right? So that is why whenever this constraint is implemented in your code or while solving your problem by hand, you need to consider this equation, and you can only assign one decision variable as 1, other as 0. So, writing for the same constraint for the department B, it should be x b L1 plus x b L2 equals to 1. Okay. Similarly, the second constraint is each location gets exactly one department. So, you have assigned one department to one location. Now, you are doing things other way, right. So, this is x a L1 plus x b L2 equals to 1, and the other constraint is x a L2 plus x b L2 equals to 1. So, what is the difference between this constraint and this constraint is that here in your first constraint, what you are trying to do is each constraint like this one is assigning one department to a particular to one of the location out of the two available, right. Here what we are doing is, in this constraint what we are doing is we are assigning a, a single department to a particular one location. So, when we evaluate all of these four constraints, only one department will be assigned to one location, right. And finally, the binary decision variable, we need to constrain them as well mathematically. So, all of our x I comma j can only be 0 comma 1. So, this we also need to specify. Now, if you solve this whole linear formulation, then the next step is your solution, right. So, let us say if A is assigned to L1, then B is at L2, right. So, the cost is you need to multiply F into D, right. So, if you go backwards and you see that if A gets assigned to L1, then your cost is 30, and if and the same cost are involved here. So, you can write 30 into distance is 10 between these two things plus same thing 30 into 10, right. So, this cost is 600. Now, if other possibility is if A is assigned to L2 and B is at L1, again the cost will be 600. Why? Because we have symmetric matrices with the same values, but if you change these values and you will get different kind of results, right. So, you have only two solution, that are two possible solutions here, but these possible solutions could be 200, 2000 as well. So, searching out of those multiple solutions is a critical task. And the third possibility is not allowed here, which is A and B both gets assigned to a single location. So, our constraints will not allow this, not allowed. So, in this example what we have seen is that we have defined an objective which was to minimize cost. Since both of these costs are similar, so any of the possible solution is an optimal solution, right. But let us say in your second solution, instead of 600 it was 500, then out of these two solutions you will choose this one if your final cost is 500, which is less than 600, right. So, these are the different kinds of possibilities that will appear in larger problems. In constraints, we have defined some constraints. These are your assignment rules. Where will these materials and locations get assigned? So, these rules are important in these kinds of situations. And then we have also introduced and used these binary decision variables. So this was a toy problem to make you initiate into these kind of problems in industrial engineering. Now let us understand what are exact solutions, and we have already seen in the course different kind of search algorithms and other approaches to find the solution space, right. So exact solution, usually for these problems we first formulate the decision variable, right, the constraints and objective function. Then we can utilize whatever we were doing in these three steps in this small problem. We can perform these steps by using different kind of solvers. Solvers could be Cplex. These are the industry standard solvers that are usually used. Gurobi. They can solve linear and non-linear problems, right? And they guarantees the optimal solution. If an optimal solution exists. So usually when we try to develop the mathematical formulation for these kinds of problems, sometimes it may happen that there are no solutions for your problem. So this can also happen. So that is why these kind of solvers specify if your problem statement has a particular has the feasibility of finding a solution, then they try to find the optimal solutions by utilizing their own algorithms, right. Now these kind of solvers works well for small to moderate size problems, but the solution space grows exponentially very easily. So in those conditions, these solvers may not provide optimal solution for these large solution space. Okay, and these kind of problems are usually known as NP-hard problems. These formulations easily create these NP-hard kind of problems, right. So let us now talk about heuristics and meta-heuristics, because we now understand that there are possibilities of finding exact solutions in some kind of problems, but usually when we increase our problem, when we try to develop a larger mathematical formulation for a problem, then the solution space increases and we need to look towards different kind of approaches that may provide a better solution easily, right. So to do that we need to understand what are heuristics and meta heuristics. So heuristics are problem specific strategies and they are designed to quickly find a good enough solution. Since these are problem specific strategies, they will give you a good enough solution, but maybe the best solution that is possible in a problem formulation is not yet available for you, or you may need to extend the same strategy to keep on finding that best solution. But to find a good enough solution easily and in a in lesser time, you can utilize heuristics, right. So the nature of heuristics could be thumb rules, greedy methods, or local search. So we have talked about search algorithms in the course, right? Scope remains in specific problems, and since they are created for specific problems, they may not generalize well for other problems. So they are problem specific in nature, right? Now they can find solutions quickly, but may remain stuck in local optima, right? So we have already talked about this local and global values. So let's say in your gradient descent type of algorithms where you are trying to find the best possible value. So if your algorithm has stuck into some kind of local values that looks optimal, then it will not try to find the other values that may give you the best overall performance for the system, right? So these heuristics can stay stuck in your local optimum. So examples of these kind of heuristics could be your nearest neighbor, for traveling salesman problem, or the shortest processing time algorithm for scheduling problems. So in the last lecture we have looked into how this SPT algorithms work, right? And this was actually a heuristic. Now let us talk about meta heuristics. So these are higher level frameworks that are guided by randomness and adaptation. Now the major thing about meta heuristics are they are problem independent. So these heuristics were specific for the problem, but if you understand a particular framework, then what you need to do is just portray the same framework and convert it into your problem. That is why they are problem independent. They are also flexible and they can explore and exploit the solution space, right? These algorithms can be applied to NP hard problems. Now these meta heuristics don't guarantee optimality, but are usually very near to global optima. So, example is your genetic algorithm, which we will learn today. Now, let us start with the genetic algorithm. So, this is a family of search and optimization algorithm, and these usually metaheuristics are inspired. It is also a heuristic, but it is inspired from natural evolution. So, these GAs are inspired from natural evolution. So, GA is good for problems with large number of parameters. So, let us say in your facility layout example, we considered only 2 departments and 2 locations, but what if there were 200 departments and 200 locations? So, in those kinds of examples, you need to implement different kinds of heuristics, and GA is a very good option for that. And GA can also solve complex or non-differentiable functions. Okay. So, this analogy with natural evolution helps in finding better solutions for search or optimization problems in less time. Okay. So, let us stop today, and we will continue understanding what are the different steps of while we try to implement genetic algorithms and how are these algorithms get implemented. Thank you.